Right. To start with our study on the assertion languages that are being developed as industry standards, we first look at the scope of applicability of assertion based verification methodology in the different parts of the verification flow. So, at the lowest level of granularity we have the modules, and then we have the blocks which are collections of modules, and then we have the integrated design which is the complete chip. So, the assertion verification is done using two styles. One is the static or formal methods, which we shall study in the future lectures, and then we have the dynamic analysis, which essentially monitors the properties over simulation runs. So, most of the modern simulators support the use of assertions. So, you can write the assertions in these languages, and then when simulation is taking place, the simulator is also monitoring the truth of these properties over the run. So, in the module level, formal is becoming very popular, because you can verify the properties in quick time and there is no state explosion, there is no capacity issues there. But as you go up the hierarchy to larger and larger granularities, we are increasingly unable to apply formal methods because of the capacity problems of these methods. So, when we discuss these methods, it will become apparent, but we must understand that assertions are not built only for formal verification. They are written for putting in checks, whether that is verified through formal or whether that is verified through simulation, does not matter, but they are written almost at every level of the design hierarchy today. So, the leading chip design companies use assertions everywhere, from the full chip level to the module level. Okay. So, if we look at the industry standards, so there are some predecessors who came up with their own languages, and then slowly those got imbibed into the standards committees. So, the original ones were Sugar from IBM Haifa. So, that is one language. Then Intel had its own language called ForSpec, and Synopsys had a language called OpenVera Assertions. Now, there is a body called Accelera, which is a consortium of companies which works on the language standards. So, they started committees on developing the assertion language standards, and today there are 3 different standards that are available in the industry. One is called PSL, or property specification language. This language supports both branching time and linear time properties. Then we have SystemVerilog assertions, which is part of the SystemVerilog standard. SystemVerilog is an extension of Verilog that we studied previously, and which has much more enhanced test bench construction facilities, and there are some nice constructs for developing test benches. And the third standard is a library called OVL, or Open Verification Library. This is a collection of simple monitor libraries in Verilog that can be stitched together to monitor more complex behaviors. So, the difference between this OVL and the other two is that these are property specification languages. The checkers for those properties are separate, they are not part of the specification, right. So, the simulator or the formal tool is going to check those properties, right. On the other hand, OVL is a library. So, it is like that you have the monitor already written, you just fit in the parameters and plug it in with your simulation, right. So, it is like a pre-designed monitor, get it. Now, all 3 of these have been developed by Accelera and then handed over to IEEE. So, PSL has become IEEE 1850 PSL. This is the new this is the standard that is there currently, it is the IEEE standard, and SVA, the SystemVerilog assertions, is a part of the IEEE 1800 SystemVerilog standards. Right. So, these are available in the IEEE website, the complete standards giving the complete syntactic and semantic description of these languages. Now, so we are going to look at SystemVerilog assertions. Right. I mean, there is no particular reason why we choose SystemVerilog assertions. We could as well have looked at PSL, but I mean, rather than learning two of them, we just decided to focus on SystemVerilog assertions. Now, when we study SystemVerilog assertions, the first thing that we have to understand is where is this signal value sampled. See, there is a simulation semantics of SystemVerilog which we studied previously. There is a sequence in which SystemVerilog is going to execute the events, right. So, non-blocking assignments, blocking assignments, the structural part, the triggering constructs, there is a scheduling semantics. Now, we must understand that where is it sampling the signal values for the assertions, because the assertions need to read the signal values. So, where is it going to do that? So, if you look at the SystemVerilog scheduling semantics, then these are the ones which we have seen previously, the active, the inactive, then this is NBA stands for non-blocking assignment, and this is where the non-blocking assignments are done. Then this is immediately after the non-blocking assignment, which when you are picking up the events that were triggered by doing the non-blocking assignment. So, the ones that we need to look at is this preponed. This preponed is something which is happening at the beginning of the clock cycle. See, this is at the beginning of the cycle, this is being done. Then there is a place where you are reading in the values. See, this is at the end of the cycle, right, and this is a place where you can react to that. Okay. Now, let us see some examples of that to get this clearer. The preponed part, so these three are the ones which are relevant for the assertion checking, right? That is why they are in red. Preponed is where it allows for user code to access data at the current time slot before any net or variable has changed state. Now, what does this mean? Remember that that any simulator is going to support certain callbacks. What are those callbacks? There are specific steps in the simulation cycle where you can insert a callback. Now, inserting a callback means that when the simulator reaches that point in its algorithm, it is going to call your function, right, and there you can do things like reading the values of the variables and things like that. So, preponed is one point where an user defined function can be called, and there you can read the values at the beginning of the simulation cycle. Before the simulator has taken any steps to update any variables, you can read the values, right. Now, see, remember that our assertion checkers will be built on top of the simulator. So, it has to have access to the variable values at specific points in the simulation cycle, right. So, this is a preponed, it allows for user code to access data at the current time slot before any net or variable has changed state. Then we have the observed point where we can evaluate property expressions if they are triggered. This is where the property expressions will be evaluated by the simulator at the observed. We are going to see in a timing diagram where it is going to take place. And then there is this reactive part. This is where it evaluates the pass and fail codes of the property. So, for each property you can have certain code to say what you will do if the property matches and what you will do if the property fails. So, it could be a simple display message, or it could be some kind of action that you take as a result of that. Whatever it is, that action, whether you print a display message that this property has failed or something, that is going to execute in the reactive phase, right. So, is it clear what these three different points indicate? The first point is where you read everything, you can read things before the simulator has done anything. The observed point is where the assertions are evaluated at the end of the cycle, and the reactive phase is where the corresponding actions for the pass or fail of that assertion are taken up, right. Now, look at this picture. So, if you look at the cycle, then see that the signals are sampled at the end of the cycle. This is very important for assertion checking. We are sampling the signals for the assertion at the end of the cycle. After everything is stable, everything has stabilized, there is no other events that are there, we are at the end of the cycle, you sample the signals there, right. And this is the period, this is the input skew, which is implicitly negative, because this is the time period where no further variables should change. And again this is the output skew, this is where no further signals should be changed. You can read your values here also after the simulation cycle has passed, and the signal driving will start after this point. So, this is the preponed region and this is the observed region, right. Is that clear? So, if you look at this, then the value of request at clock tick 5 is 1, not 0. See, at clock tick 5 the value that you are reading is here. So, you can assume that everything changes in the next cycle. So, if you are at the beginning of the next cycle, your value here is 1. So, even though we may draw it like this, you can assume that this dotted line is a little to the left, right, because remember there is a point of time where nothing should happen. This driving of the signal to 0 takes place after that boundary, cycle boundary, right. So, similarly value of request at clock tick 9 is 0, not 1, clear, right. So, at these edges always read the value which is just the previous one, that is the one that the assertion will use. Now, let us that is how the scheduling is, the sampling is done for the assertion checking. So, now let us see how we can encode the properties that we wrote earlier for our memory arbiter in the SystemVerilog assertion language. So, we are going to make a quick tour of SystemVerilog assertions around this example and then go into some more detailed features of the SystemVerilog assertion language. So, we will first code these properties in SVA and then we will see how to bind these properties with the interface of the DUT. How do we actually connect these properties with the simulator. So, these are our properties. Let us start one by one. This is the SystemVerilog assertion for the property P1, which says that whenever we have R1, then in the next cycle we must have G1 and next to next cycle we must have G1. Now, see here always this says property P1 at passage clock, if R1, then in the next cycle G1 and in the next cycle G1. Now, see we did not put XX here, right. So, this is called a sequence expression, this part is called a sequence expression, and that is because unlike this where this is a term and this is a term, these are two independent terms, each interpreted from the current cycle. So, this is from the current cycle next G1 and this is from the current cycle next to next G1, right. But here this is one single sequence expression. It is not two different expressions. It says next cycle G1 and then next cycle G1. So, G1 followed by G1. Is that clear? There is a difference between writing it with an and the way that this sequence expression is written. Clear? This one says in the same vein that at passage clock not G1 implies G2, right. So, in this implication you see that if I just keep the implication, that it means that implication in the same cycle, that is unlike here where we had hash 1 which indicated that it is in one cycle after this, right. Then also look at the way we use not here, right, and this is not the same as the not that we use in Verilog, which is the tilde, right. So, this is the exclamation used as not. At passage clock not R1. So, what does this says? That if R1 is low for 2 consecutive cycles, then G1 must be low in the next cycle. Now, again look at the interesting thing here, that we have not R1 and then hash 1 not R1. So, this says that R1 is true in 2 cycles, not R1 is true in 2 consecutive cycles, implies that in the next cycle following this match not G1 must hold. Now, see we did not have XX not G1 here, we are just having hash 1 not G1. Now, see the difference between these two is, see this one at if this matches. So, let me just write this down. So, I have not R1 and X not R1 implies XX not G1, right. Now, what does this mean? That I am suppose in a path, suppose I am here. So, I am saying that not R1 must hold here, if not R1 holds here, and X not R1 holds here. So, R1 must hold here, X not R1 must also hold here. We are talking about everything which holds here, right. Then XX not G1 must hold here. So, everything is with respect to this state, with respect to this state. Now, these are 3 independent properties. This one is true here if R1 not R1 is true here, R1 is low here. This one is true here if not R1 is true in the next cycle, and this one is true if not G1 is true in the next cycle. Now, compare that with the sequence expression which says or the expression which says R1 hash 1 not R1 Now, this says that not R1 will hold here. So, it is a sequence expression. So, this is one property, right, this is one expression. So, R1 not R1, not R1, not R1. Then here we have a match. Suppose I call this sequence expression S. So, match of S, right. and then wherever the match of S has taken place, from there we start the match of this. So, from here in another hash S1 I must have not of G1. Okay. So, you see that unlike these where all three were being interpreted from here, this one is being interpreted from here, from this wherever we got the match, not from here. If it was to be interpreted from here, then we would have to give 2 hash S1s or hash S2, right. So, please keep in mind that this slight difference in the way the interpretation is taking place. And the last property is simple, at passage clock not G1 or not G2 end property. Now, this is how the assertions are going to get integrated with the rest of the design. Now, remember that in these assertions we have used some variable names like R1, G1, etc. right. Now, it is not necessary that the module that we are verifying or the design under test, DUT stands for design under test. So, the design under test that we are verifying, it is not necessary that the signal names will be the same in the module. So, what I am calling R1 here may be called as REQ1 in the DUT, G1 in the DUT may be GNT1, right. What bind does is it binds that which variable of this is being bound to which variable of the assertion, right. That mapping between the net names in the DUT and the variable names used in the assertions is done through the bind, right. And once that bind is done, then the simulator can check those assertions by monitoring those signals which are being bound with the assertions, right. That is the link with the assertions and the DUT, right. And in SystemVerilog there is a notion of an interface. So, see in previously when you studied Verilog, you saw that when you are instantiating modules, you are instantiating the modules with arguments, right. Those arguments are positional arguments. So, in the sense that the first argument is actually matching with the instantiation that you had, the argument that you had passed in the instantiation, right. So, that is how the implicit wires were getting connected. Are you following what I am saying? Huh? Now, when we are talking about interfaces in SystemVerilog, we will see later on in one of the lectures that an interface is a separate object where you define that between these two blocks what is my interface going to be, and then you instantiate that interface as an argument. This helps in having some kind of uniformity when many different blocks are sharing the same interface. For example, if you have a bus, that bus there can be many different modules which are interfacing with that bus. So, you define the interface for that bus only at one place, and every module which wants to interface with that bus will have that interface as one of its arguments, right. That way you make fewer mistakes. So, that is why this picture shows that there is an interface here, and the assertions are actually using the variables that are specified in that interface, and we bind that with the DUT, right. So, it is the interface which is getting bound with the DUT. Now, let us see the example. So, here first thing that we will do is see these properties is a property, right. This is one of the properties which we wrote down just now. This is another one of those properties, and the other properties are also there. So, we are putting all of them in an interface definition. So, this is an interface arbiter checker interface, where we have all of these as inputs. Now, that is natural, right, because the assertion checker will not drive any signal, it is only going to read all the signals and interpret whether the assertions are holding or not. So, everything is an input to the arbiter, the interface. Now, let us look at this property. So, we first define the property, and then this is where we specify whether the property is an assert property or an assume property. Properties can be of 3 different types. They can be assert properties, where you are saying that the design must satisfy the property. You can have an assume property, where you say that the design assumes that the property is true. So, if the assumption fails, then you do not check any of the assertions, right. And the third is a cover property. We are going to come back to these 3 types of properties with examples. So, for the time being, let us see that, say that this is this statement assert property P1, this statement is actually telling the interface that this property has to be checked, and if the assertion fails, then this is the action that is taken. Remember that we were talking about pass fail codes. So, this is the fail code. So, when the assertion fails, we display property P1 has failed, right. Now, in this interface, so we are specifying all the properties, and we are also writing down the pass fail codes for each of them. Then this is the test bench. In the test bench, let us see what we are doing. We are instantiating the arbiter, right. This is the module arbiter. Then this is the duty, by the way, this is the design under test for us. Then we are applying clock here, right, and then there is the rest of the test bench which drives the request scenarios. So, the rest of the test bench code is where the arbiter gets the requests, right. This is the top module which has the test bench and the instantiation of the arbiter, of the duty, right, and this is the clocking block. Now, to bind the interface arb checker with the test bench, we use the bind statement. So, this says bind the arb checker arb c g1 g2 r1 r2 clock with the top. Now, this statement is actually binding this with this top, right, all right. And that completes the complete specification of the assertion. So, we have the assertions, we wrote them inside the interface, and then we bind the interface with the test bench, right. Now, if you run simulations, then the simulator will automatically check those assertions during the simulation run. So, having seen this whole gamut of how we write the properties and then binding it with this thing, let us look into some more details of the SystemVerilog assertion language. So, here are some simple examples. When we write, we have already seen what #1 R1 means. It means R1 is true in the next cycle. #0 R1 means R1 is true in this cycle itself, right. #5 R1 means R1 is true exactly after 5 cycles, and #5:9 R1 means R1 is true sometime between the 5th and 9th cycle. So, you see that the similarity with the time deltial operators, that #1 R1 is the same as x R1 that we saw in LTL, #5 R1 is the same as f55 R1, and #59 R1 is the same as f529 R1, right. what is the meaning of the following sequence expression? It says A followed by B or C, and that B or C should hold sometime between the 1 to 5 cycle, and wherever B and C holds, from that after 3 clock cycles D should hold, right. Now, instead of writing this as a single sequence expression, we can break it up into multiple sequence expressions. So, now see, I first define a sequence S1 as B or C hashes 3D, right, and I name that sequence as S1, right. So, every sequence has a name. So, I name that sequence S1, then when I define sequence S2, I use A hashes 1 colon 5 S1, right. So, see, this S1 is actually this thing is my S1, right. So, this kind of defining subsequences helps you to structure the assertions nicely, so that the individual assertions do not become too complicated and long. The next thing that we did not see in LTL, but we are seeing here is the notion of repetition. So, the first type of repetition that we are going to look at is called consecutive repetition. So, P star 5 matches when 5 consecutive states satisfy P. So, if you have P, 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 P in 5 consecutive states, then we say P star 5 is true, has matched. Then P star 5 is matched. When you have P star 3 colon 5 and then hashes 1 Q, this means that there are k consecutive matches where k is between 3 and 5. Oh, I missed the P here. So, k consecutive matches of P followed by Q. Okay. So, there should be at least 3 matches of P, and then Q must hold in the next cycle, right. We can have 3 matches or 4 matches or 5 matches, but after that Q must hold. If you put a dollar here, the dollar indicates end of simulation, right. So, if you write 3 colon dollar, then that means that it is going to repeat at least 3 times and then Q must hold. Now, see, at least 3 times means that it can match as many number of times until end of simulation. Now, if by the end of simulation Q has still not satisfied, then it will indicate at the end of simulation that look, this property was not finally matched, because we did not have a refutation, in the sense that we did not end up by having not P and not Q, but we did not get the match also, in the sense that we did not get Q. So, it is going to report that. On the other hand, if you get Q somewhere and P holds on all the states preceding that, then this is going to match, provided that the number of matches of P is at least 3. Right. Okay. Now, before we proceed further, there is one important thing to note here, that in LTL you can have things like this, that suppose you have P until Q, okay, until say R and XR. Suppose take this property, right. Now, what does this mean? This means that on every path, every state on the path, this means that somewhere we must have R, and in the next state also we must have R. So, this is where your R and X R is satisfied. So, somewhere in future R and X R must hold, and all states preceding this P until Q must hold. So, that means that P until Q must hold here, P until Q must hold here, P until Q must hold here, right, in all of these. But there is a possibility that the match of P until Q takes place much later on, in the sense that it can be possible that we have P here, 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 P here, and then we have Q here. Now, see what is happening here. P until Q is true here because it holds, Q holds here and P is true all the time. So, P until Q is true here, it is true here, and then here you get R and X R. But if you proceed from left to right, if you are doing simulation, for example, when you have reached here, you still do not know whether P until Q is going to hold or not. You still do not know that, because it may hold in future, it may not hold in future. We may not get a Q in future, right. So, therefore, that problem is there when you are checking LTL properties here. Now, in SVA you cannot do things like this. In SVA, one part of the sequence expression must match before you move to the next one, right. So, when I have that something like A hash 1, A hash say 1 to 5 B, and then I have a implication, then I have hash 8 some C, right. Then you see from left to right we must first match A, then after one cycle we must match A, then within the next 5 cycles we must match B, and only when this has matched, from that point onwards we are going to start matching this one, right. So, if we did it for the LTL, it would have meant that you first match up to Q and then start matching this R and X R, which is not what the LTL property says, right. But in SVA every property is like that, that you have to first match the antecedent of the implication, wherever the antecedent of the implication matches, from there onwards you start matching the consequence of the implication, right. So, the request, let us come back to this example. So, suppose we want to say the request R must remain high until the grant G is asserted. So, we can write that as R implies then the request remains high until the grant comes. What does this mean? That request must remain high until somewhere you get hash 1 G, right. The LTL property P until Q is equivalent to P star 0 colon dollar hash 1 Q, right. Now, when we talk about consecutive repetitions, the meaning is that these repetitions of B, for example, here the repetition of B must happen in consecutive cycles. So, in which 3 cycles is B true? It is true in it is true here, okay. A is true here, So, the matching starts from here, let us say, where we get A, then we get B here, we get B here, and we get 3 consecutive B's, right. And then in the next clock tick we check for C and we find C is high, right. So, this is called consecutive repetition, because all this is 3 consecutive matches of B, which is this operator. Now, compare that with another repetition which says the go to repetition. Now, what this says is that P star, this go to 5, the match of Q at some time t is preceded by 5 matches. So, we must have 5 matches of P before we get Q, but those 5 matches need not be consecutive matches, right. And but there is a constraint that the last match should be followed by Q in the next cycle. See, this says there has to be 5 matches, those 5 matches need not be consecutive, but as soon as you get the 5th match in the next cycle, Q must hold. So, now this says, suppose we want to say that in some bus transfer, the transfer must be aborted if the transfer is split more than once. So, typically what happens is, in bus transfers there is a difference, there can be a difference in speed of transfer between the master and the slave. So, if the slave is not able to produce the data within time, then it can split the transfer. It says to the master that hold on, I am not yet ready. So, that is a split transfer, right. Now, you may say that if the split hold is done more than once, then we will abort the transfer, right. That means, if we write it like this, that split 2 repetitions, go to repetitions followed by abort, this means that as soon as you have 2 splits, may not be consecutive, during the whole transfer, if you have 2 splits, then immediately abort the transfer, right. That immediately abort the transfer is what warrants us to use the go to repetition, right, that immediately in the next cycle abort should take place. Okay. So, this is an example which says that instead of B star 3, we have put B this non consecutive go to repetitions. So, let us look at this A matches here, right. Then we have one occurrence of B here, we have another occurrence of B here, there is nothing that happens here, there is nothing that happens here, the third occurrence of B happens here, right, and immediately on the next cycle we check C, right. So, first occurrence of B, second occurrence of B, third occurrence of B, as soon as you have got 3 B's, then check C, right. The last type of repetition is called non consecutive repetition and is written like with star equal to 2. Now, this is the same as the previous one, except that we do not have the constraint that the abort has to take place in the immediate next cycle. So, it says that at least after one cycle, right. So, the abort can take place a few cycles later also, there is no problem with that, right? That is the only difference here. That is called, this is called the non consecutive repetition. So, this is an example of non consecutive repetition. So, again let us see, we match A here, then we get the first match of B here, second match of B here, then we get the third match of B here, and then in the immediate next cycle C is still not high. So, if we had the go to repetition, we would have said that this is an error, but for non-consecutive repetitions we wait until we get the C, and at this point you say that the property has matched, right. So, we shall quickly look at two other logical operations. One is the AND operation. How do we take AND of sequence expressions? So, A hashes 1 B and A hashes 1 B hashes 2 C. Now, the meaning of the AND is very simple. Meaning of the AND is that in the trace this must match and this must match, period. Now, which is the point where we are going to say that the whole thing has matched, right. So, let us look at this example. So, we had A here, then hashes 1 B. So, here the first this part has matched, right? This part has matched here, the match of this is here, the red arrow. Then look at the second one. For the second one also the match started here. So, we had A here, we had hashes 1 B, then we look at hashes 2 C. So, this is next to next, right. So, here we do not get hashes 2 C, right. For this you do not get the hashes 2 C, right, because we would have expected that we have B here. So, here we should have had C, but we do not get C here, right. So, this is one failure. Now, where does it match? It matches if you start the A from here. So, suppose A matches here, right, then hashes 1 B matches here, oops, not that, let me start once again. A matches here, then B matches here, right, in both these expressions. So, this part matches here, right. Now, let us look at the match of this hashes. So, A matches here, B matches here, and then hashes 2 here we get C, right. Okay. Now, this part matches here in this place. Now, when both of these have matched, then we can say that this whole thing has matched. So, the match point of this whole sequence expression is this, right. That is not the case when you have OR. In case of OR, when any one of them has matched, you get a match. So, you see that here you had A, then here you had hashes 1 B. So, you get a match of the OR here. Then again you have A here, you have hashes 1 B here. So, you get another match here, right, and then you get A here, you get hashes 1 B and hashes 2 C here. So, you get another match here, right. So, these are all matches for this. Do you follow, right? One last thing that we have to look at is the intersection. We will stop with this one. The intersection says that it is used when both operand expressions are expected to succeed. N times of the operand expressions must be the same, and length of the two operand sequences must be the same, right. So, let us look at this. The end of the two operand sequences must be the same, right, the length, right. Now, if that does not happen, then there is no match, right. So, it is here that everything matches. Why? Because if you start from here, we get A here, then if you take 1 to 3. So, let us take the case for 3. So, 1, 2, 3. Here we get B. So, this one matches here, and this one also matches, because you have A, then you have hashish 1 B, then you have from here after 2 cycles you get C, right. So, this one also matches here. Now, because they all both of them match at the same place, so there is a match of this intersect, right, otherwise there is no intersect, right. So, we conclude here, and in the next classes we are going to look at some more features of SystemVerilog assertions and some ways of designing these properties.